change that to greater than or equal to, I think. But it's the same song and dance, right? It's still the case that this is absurd. You can't have the product of two natural numbers, which are not both 1, be less than or equal to 1. So there you go. All right. So we do actually want to give those kind of careful, like I just wrote in the green, that's the kind of thing we would like to show in this course. But if you have an intuitive idea about what's right and you write it down, you can't provide those details, you might still get partial credit. It kind of depends on the problem. But anyway, we'll fight those battles as we come to them, okay? We stick with today's battles. All right, so every positive integer n has factorization n is 2 to the k times m, where k is greater than or equal to 0 and m is odd. An odd integer larger than 1. We're going to let this be the claim. In other words, every positive integer can be factored into 2 to some power times an odd integer. Interesting. So we're going to give a proof by complete, which is also known as strong induction. The base step, n equals 1, 2 to the 0 times 1, p of 1 is true, because 1 is an odd integer, and k is equal to 0 here. Induction step. We're going to suppose, come on. All right. Fighting with my papers here. Suppose that j has a factorization of 2 to the kj times mj for j equals to j being some number between 1 and n. And so when I say has a factorization, I just mean that j equals to that, all right? Consider n plus 1. Well, if n plus 1 is prime, then n plus 1 is 2 to the 0 times n plus 1. And, since we're assuming that n is, well, anyway, could n, I guess I should worry, could this prime be even? If this is even, that's the n equals 1 case, but we've already taken care of that, so there's nothing to worry about. So we can justly assume here that n is greater than 1, right? If n is greater than 1, then certainly n plus 1 is greater than 2, which is to say that if n plus 1 is prime, it must be an odd prime, right? Because the only even prime is 2, actually. Okay. All right. So if n plus 1 is not prime, then n plus 1 is equal to a times b. N plus 1 is composite, right? It can be written as a product of a and b, both larger than 1, where a and b are both less than n plus 1, right? So a comma b is less than n is also clear, as if we did have a equals to n and b less than n plus 1, without loss of generality, I can assume that one's n and that one's less than n plus 1. That would give us trouble, because that would give us n plus 1 equals to nb, where that's n times 1 minus b equals to minus 1, where n and 1 minus b are both positive. Well, we can't have the product of positive numbers being minus 1. That's a contradiction, right? So we can justly assume that we can't have one of these equal to n, right? Okay, so since a is less than n, we also have that a is equal to 2 to the k times m by the induction hypothesis. And since b is less than n, and I really should say since here, b is less than n. Put that in right there. Sorry about that, guys. B is equal to 2 to the j times m prime, right? Because, and I shouldn't use j there because it's using a different sense. I gotta change that j to a j prime. Sorry about that, guys. I don't want to reuse j it already has a meaning before. So n plus 1 is 2 to the k times m times 2 to the j prime times m prime, which is 2 to the k plus j prime, mm prime. But here m and m prime are odd, and k plus j prime is greater than 0. But the product of an odd with an odd number is an odd number, so we could say m prime prime is mm prime, and so what we have is n plus 1 is 2 to the k prime prime, m prime prime, which is the induction hypothesis for n plus 1. And so by proof by complete induction or by strong induction, we conclude that Pn is true for all natural numbers n. So you want to use strong induction or complete induction when the natural proof involves several levels of the statement. And so there are various examples that appear like that. If I assigned you the Fibonacci problem, the Fibonacci problem is another one where the strong induction is wise, because it involves n minus 1 and n minus 2 at the same time. So like you end up needing strong induction most naturally. I say most naturally because the fact that well-ordering principles, weak induction and strong induction, are equivalent in the context of the natural numbers, the usual natural numbers, means that any proof you could write for any one of these could be like twisted into a proof for the other one. The question is just like what's easiest. And so some problems, regular induction's easiest. Other problems, strong induction's easiest. Other problems still, the well-ordering well-ordering principle is most natural. Well-ordering principle. Every non-empty subset of the natural numbers has a smallest element. This is the WOP, the well-ordering principle. So here's an example. Suppose we have n is a natural number greater than 1, and suppose n is not prime, and let S be the set of all factors of n which are not 1. Since n is composite, n is equal to AB for some a and b, and AB is greater than 1. Excuse me. Since AB is an S, that means that S is non-empty, right? So S is a non-empty subset of the natural numbers. We can apply the well-ordering principle. It says that there exists S naught and S such that S naught is smaller than everything else in the set, right? And we're going to argue that that S naught has to be prime. So suppose S naught is not prime. If S naught is not prime, then there exists A naught B naught with A naught B naught greater than 1, such that S naught is the product of these two natural numbers. But then A naught and S naught, A naught and B naught are less than S naught, right? And yet n is equal to Ks naught is equal to K A naught B naught, which says that A naught is a factor of n, which means A naught is an S. But A naught is less than the smallest element in S, which of course contradicts S naught being the smallest element, which means that, in fact, this assumption that S naught was composite was false, which is to say that S naught is prime. And so the well-ordering principle gave us a pretty easy proof that any natural number has a prime factor, right? In fact, therefore, any n greater than 1 is either prime or has a prime factor, which shows that any n greater than 1 has a prime factor, because if it's prime, then it's its own prime factor, right? So any way you slice it, any n natural number greater than 1 has a prime factor. Once you know that, it's actually not too much more trouble. I won't do it here, but I'll just tell you that the fundamental theorem of arithmetic says that any natural number can be rewritten. I mean, can it be expressed as a product of prime powers, which is unique up to the reordering of the prime powers. These are distinct primes, is my assumption. Product of distinct prime powers. So there's that. All right, finally, so everything has made sense up to now, I hope. Ha ha ha. Maybe, maybe not. Try your homework, see how that goes. I will leave you with this rather disturbing example due to Joel Cohen, who apparently gave this in a, I'm not sure what it was exactly, but on the nature of mathematical proof. This is reprinted in a random walk in science Crane and Rusek, I guess, 1973. I found it in the Wikipedia article on induction, but anyway, here's the proposition. A set of n horses has horses of one color. I mean, this doesn't seem right, right? But all right, let's see if we can prove it with induction. N equals 1, certainly a set of horses where you just have one horse has a horse of one color. I believe that, right? If you got one horse, the horse has one color. And we're assuming that the horses are not like, we're assuming monochromatic horses, all right? So if you're thinking about a horse that's like white on one end and black on the other, you're misunderstanding the conversation here. Assume monochromatic horses, all right? Great. Suppose inductively that any set of n greater than 1 horses has horses of one color. And we can just number them for the sake of discussion, 1 through n plus 1, right? So take S to be the horses 1 through n. By the induction hypothesis, they have the same color. Let's say red for conversation's sake. And let T be the horses 2 through n plus 1, right? And then, again, by the induction hypothesis, this is a set of n horses. And since it has, some commonality with the other one, right? The S and the T, they overlap at 2 through n, right? That must mean that these are also red horses, right? But then that shows that all of the horses 1 through n plus 1 have the same color, which means that by proof by mathematical induction, we can conclude that any set of n horses has just one color. And I will leave you with the question, what? So when we talk next, maybe we can talk about why this is not right. Where's the error in this proof? I'll leave you with that. Thank you.